The Monty Hall problem is a brain-teaser, in the form of a probability puzzle, loosely based on the American television game show Let's Make a Deal and named after its original host, Monty Hall. The problem was originally posed in a letter by Steve Selvin to the American Statistician in 1975. It became famous as a question from a reader's letter quoted in Marilyn Vos Savant's Ask Marilyn column in Parade magazine in 1990. Suppose you're on a game show, and you're given the choice of 3 doors. Behind one door is a car, behind the others, goats. You pick a door, say no. 1, and the host, who knows what's behind the doors, opens another door, say no. 3, which has a goat. He then says to you, do you want to pick door no? 2, is it to your advantage to switch your choice? Vos Savant's response was that the contestant should switch to the other door. Under the standard assumptions, contestants who switch have a 2/3 chance of winning the car, while contestants who stick to the choice have only a 1/3 chance. The given probabilities depend on specific assumptions about how the host and contestant choose their doors. A key insight is that, under these standard conditions, there is more information about doors 2 and 3 that was not available at the beginning of the game, when the door 1 was chosen by the player. The host's deliberate action adds value to the door he did not choose to eliminate, but not to the one chosen by the contestant originally. Other possible behaviors than the one described can reveal different additional information, or none at all, and yield different probabilities. Many readers of Vos Savant's column refused to believe switching is beneficial despite her explanation. After the problem appeared in Parade, approximately 10,000 readers, including nearly 1,000 with PhDs, wrote to the magazine, most of them claiming Vos Savant was wrong. Even when given explanations, simulations, and formal mathematical proofs, many people still do not accept that switching is the best strategy. Paul Erdos, one of the most prolific mathematicians in history, remained unconvinced until he was shown a computer simulation confirming the predicted result. The problem is a paradox of the veridical type, because the correct result is so counterintuitive it can seem absurd, but is nevertheless demonstrably true. The Monty Hall problem is mathematically closely related to the earlier 3 prisoners problem and to the much older Bertrand's box paradox. The paradox. Steve Selvin wrote a letter to the American Statistician in 1975 describing a problem loosely based on the game show Let's Make a Deal, dubbing it the Monty Hall problem. In a subsequent letter, the problem is mathematically equivalent to the 3 prisoners problem described in Martin Gardner's Mathematical Games column in Scientific American in 1959 and the 3 shells problem described in Gardner's book, A Hagoka. The same problem was restated in a 1990 letter by Craig Whitaker to Marilyn Vos Savant's Ask Marilyn column in Parade. Suppose you're on a game show, and you're given the choice of 3 doors. Behind one door is a car, behind the others, goats. You pick a door, say no. 1, and the host, who knows what's behind the doors, opens another door, say no. 3, which has a goat. He then says to you, do you want to pick door no? 2, is it to your advantage to switch your choice? Standard assumptions. The behavior of the host is key to the 2/3 solution. Ambiguities in the Parade version do not explicitly define the protocol of the host. However, Marilyn Vos Savant's solution printed alongside Whitaker's question implies and both Selvin and Vos Savant explicitly define the role of the host, as follows. The host must always open a door that was not picked by the contestant. The host must always open a door to reveal a goat and never the car. The host must always offer the chance to switch between the originally chosen door and the remaining closed door. When any of these assumptions is varied, it can change the probability of winning by switching doors as detailed in the section below. It is also typically presumed that the car is initially hidden behind a random door and that if the player initially picks the car, then the host's choice of which goat hiding door to open is random. Some authors, independently or inclusively, assume the player's initial choice is random as well. Selvin's simple solutions. The solution presented by Savant in Parade shows the three possible arrangements of one car and two goats behind three doors and the result of staying or switching after initially picking door 1 in each case. A player who stays with the initial choice wins in only 1 out of 3 of these equally likely possibilities, while a player who switches wins in 2 out of 3. An intuitive explanation is that if the contestant picks a goat, the contestant will win the car by switching, as the other goat can no longer be picked, while if the contestant picks the car, the contestant will not win the car by switching. The fact that the host subsequently reveals a goat in one of the unchosen doors changes nothing about the initial probability. Another way to understand the solution is to consider the two original unchosen doors together. As Cecil Adams puts it, Monty is saying in effect, you can keep your one door or you can have the other two doors. The 2/3 chance of finding the car has not been changed by the opening of one of these doors because Monty, knowing the location of the car, is certain to reveal a goat. So the player's choice after the host opens a door is no different than if the host offered the player the option to switch from their original chosen door to the set of both remaining doors. The switch in this case clearly gives the player a 2/3 probability of choosing the car. As Keith Devlin says, by opening his door, Monty is saying to the contestant, there are two doors you did not choose, and the probability that the prize is behind one of them is 2/3. I'll help you by using my knowledge of where the prize is to open one of those two doors to show you that it does not hide the prize. You can now take advantage of this additional information. Your choice of door A has a chance of 1 in 3 of being the winner. I have not changed that, but by eliminating door C, I have shown you that the probability that door B hides the prize is 2 in 3. Savant suggests that the solution will be more intuitive with 1 million doors rather than 3. In this case there are 999,999 doors with goats behind them and one door with a prize. After the player picks a door, the host opens all but one of the remaining doors. On average, in 999,999 times out of 1 million, the remaining door will contain the prize. Intuitively, the player should ask how likely is it that, given 1 million doors, he or she managed to pick the right one initially. Stibble al. Proposed working memory demand is taxed during the Monty Hall problem, and that this forces people to collapse the choices into two equally probable options. They report that when increasing the number of options to over 7 choices, people tend to switch more often. However, most contestants still incorrectly judge the probability of success at 50/50ths. Savant and the media furor. You blew it, and you blew it big. Since you seem to have difficulty grasping the basic principle at work here, I'll explain. After the host reveals a goat, you now have a 1 in 2 chance of being correct. Whether you change your selection or not, the odds are the same. There is enough mathematical illiteracy in this country, and we don't need the world's highest IQ propagating more shame. Scott Smith, Ph.D., University of Florida. Savant wrote in her first column on the Monty Hall problem that the player should switch. She received thousands of letters from her readers, the vast majority of which, including many from readers with PhDs, disagreed with her answer. During 1991, 3 more of her columns in Parade were devoted to the paradox. Numerous examples of letters from readers of Savant's columns are presented and discussed in the Monty Hall dilemma, a cognitive illusion par excellence. The discussion was replayed in other venues, and reported in major newspapers such as the New York Times. In an attempt to clarify her answer, she proposed a shell game to illustrate. You look away, and I put a pea under one of 3 shells. Then I ask you to put your finger on a shell. The odds that your choice contains a P are 1/3. Agreed. Then I simply lift up an empty shell from the remaining other two, as I can do this regardless of what you've chosen. We've learned nothing to allow us to revise the odds on the shell under your finger. She also proposed a similar simulation with 3 playing cards. Vos Savant commented that though some confusion was caused by some readers not realizing that they were supposed to assume that the host must always reveal a goat, almost all of her numerous correspondents had correctly understood the problem assumptions, and were still initially convinced that Vos Savant's answer was wrong. Confusion and criticism. Sources of confusion. When first presented with the Monty Hall problem, an overwhelming majority of people assume that each door has an equal probability and conclude that switching does not matter. Out of 228 subjects in one study, only 13% chose to switch. In her book The Power of Logical Thinking, Vos Savant quotes cognitive psychologist Massimo Piattelli Palmarini as saying, "No other statistical puzzle comes so close to fooling all the people all the time, and that even Nobel physicists systematically give the wrong answer, and that they insist on it, and they are ready to berate in print those who propose the right answer." Pigeons repeatedly exposed to the problem show that they rapidly learn always to switch, unlike humans. Most statements of the problem, notably the one in Parade magazine, do not match the rules of the actual game show, and do not fully specify the host's behavior or that the car's location is randomly selected. Krauss and Wang conjecture that people make the standard assumptions even if they are not explicitly stated, although these issues are mathematically significant. Even when controlling for these factors, nearly all people still think each of the 2 unopened doors has an equal probability and conclude switching does not matter. This equal probability assumption is a deeply rooted intuition. People strongly tend to think probability is evenly distributed across as many unknowns as are present, whether it is or not. Indeed, if a player believes that sticking and switching are equally successful and therefore equally often decides to switch as to stay, they will win 50% of the time, reinforcing their original belief. Missing the unequal chances of those 2 doors, and in not considering that 2 gives a chance of 50%, similar to the little green woman example. The problem continues to attract the attention of cognitive psychologists. The typical behavior of the majority, i.e., not switching, may be explained by phenomena known in the psychological literature as 1. The endowment effect. People tend to overvalue the winning probability of the already chosen, already owned door. 2. The status quo bias. People prefer to stick with the choice of door they have already made. 3. The errors of omission versus errors of commission effect. All else considered equal, people prefer any errors they are responsible for to have occurred through omission of taking action, rather than through having taken an explicit action that later becomes known to have been erroneous. Experimental evidence confirms that these are plausible explanations which do not depend on probability intuition.